Picture a dark room. Outside the window it is night, somewhere in Egypt or Mesopotamia, thousands of years ago. In the center of the room, there is a clay furnace, and inside it glowing coals breathe heat. A man crouches in front of this furnace. In his hands he holds a piece of strange, glittering ore. He places it into the fire. He waits. And when he pulls the ore back out, something incredible happens. From a grey, unremarkable stone emerges a gleaming, reddish metal. Copper, the first metal that people learned to extract from ore. This man does not know why this happened. He does not know what chemistry is. He has no beakers, no formulas, no periodic table. All he has is fire, clay, ore, and great curiosity. But this moment, the moment when clay and fire transform one stone into another, this is the first step in the history of chemistry. Behind this man stand thousands of years of experiments, mistakes, revelations, and wild theories. Behind him stand the alchemists who believed they could turn lead into gold. Behind him stand monks and heretics working in basements and kitchens who were not searching for the philosopher's stone, but for new paints, medicines, and materials. Behind him stand scientists who argued about what air is made of, and one of them, a French aristocrat, lost his head to the guillotine for his ideas. Behind him stand the geniuses who brought order to chaos and discovered that everything around us, from the stars to your own body, is made of just over 100 simple elements. And behind him stand the modern alchemists who turn coal into nylon, oil into plastic, and air into fertilizer. But let us not get ahead of ourselves. This story is a story of transformations. It is about how people learn to turn one substance into another, how clay, fire, ore, and courage transformed humanity from wandering tribes into the builders of pyramids, empires, and civilizations. And this story is about you and me. Because every atom in your body is the result of thousands of years of alchemical and chemical transformations. Your bones contain calcium that was once part of ancient seashells. Your brain is a complex cocktail of carbon, hydrogen, oxygen, and nitrogen that was once part of ancient forests and oceans. Your breath is an exchange of oxygen and carbon dioxide that was only discovered in the 18th century. But how did we get here? How did we move from believing that the world consists of 4 elements, earth, water, air, and fire, to understanding that the world consists of atoms that join together into molecules, and molecules create everything that exists? How did we move from alchemy, which was half mysticism and half craft, to modern chemistry, the science that creates medicines, materials, fuel, and food? And how did it happen that chemistry, which began with attempts to turn lead into gold, ended up learning to turn coal into dyes, oil into plastic, and air into fertilizer, and in doing so, changed the world beyond recognition? Let us find out, slowly, step by step, from the first fire to the latest discoveries. The first chemists did not wear white lab coats, they did not have laboratories, but they had fire, and they had clay, and they noticed that if you heat certain stones, they melt and turn into a gleaming metal, while if you heat others, they turn into lime. If you burn wood in a closed vessel, black charcoal remains. If you mix clay with water and fire it, it becomes hard and waterproof. These observations were the first chemical experiments in human history. Ancient people learned to extract copper by roasting malachite ore in a campfire. This was around 6,000 years before our era. It was the first chemical reaction in history that humans learned to control. The next step was bronze, an alloy of copper and tin. Bronze was harder than copper, and it gave its name to an entire era, the Bronze Age. Then came the Iron Age, when people learned to reduce iron from ore using charcoal. Iron changed everything. It was cheaper and more available than bronze. It was used to make weapons, plows, axes. Iron fed and killed. But people did not know why ore turns into metal. They knew how to do it, but they did not know why it worked. Chemistry was a craft, not a science. The ancient Greeks were the first to try to explain what the world is made of. They proposed the theory of 4 elements: earth, water, air, and fire. This theory was beautiful, but it was wrong. It claimed that all substances consist of these 4 elements in different proportions. The theory of 4 elements persisted for nearly 2,000 years. It was convenient, it explained many observations, but it was incorrect. Meanwhile, in Egypt, Mesopotamia, China, and India, craftspeople continued to experiment with substances. They made glass, dyes, enamels, soap, ceramics. They distilled wine to obtain alcohol. They evaporated seawater to get salt. They boiled vegetable oil with lime to make soap. They mixed sulfur, saltpeter, and charcoal to make gunpowder. They did not know chemistry, but they knew craft. And this craft was passed down from generation to generation, from master to apprentice. Then came the alchemists. Alchemy is not just an attempt to turn lead into gold. Alchemy is a mixture of chemical craft, philosophy, mysticism, and greed. Alchemists searched for the philosopher's stone, a substance that could turn any metal into gold. They searched for the elixir of life, a substance that could cure any illness and grant immortality. They found neither. But they made many important discoveries. Alchemists invented many laboratory tools: the alembic still, the alchemical furnace, the retort. They discovered new substances: sulfuric acid, nitric acid, alcohol, ether, phosphorus. They developed methods for separating substances: distillation, sublimation, crystallization, filtration. They created a system of symbols for denoting substances and processes. This system was convoluted and secretive, but it was the first attempt to record chemical knowledge. The most famous Arab alchemist was Jabir ibn Hayyan, known in Europe as Geber. He lived in the 8th century CE in Iraq. He wrote that all metals consist of sulfur and mercury, and that they can be transformed into one another. He believed that the philosopher's stone existed, and he dedicated his life to finding it. Jabir ibn Hayyan was not a charlatan. He was a scientist who tried to understand the world, and his ideas influenced alchemy and chemistry for many centuries to come. Alchemy flourished in the Arab world, and then in medieval Europe. In Europe, alchemy was connected with astrology and magic. Alchemists believed that metals had souls. They believed that planets influenced the properties of metals. They believed that gold was the perfect metal, and lead was a sick metal that needed to be healed. These were strange, fanciful theories, but they were the basis for experiments, and experiments produced results. By the end of the Middle Ages, alchemy began to transform into chemistry. Scientists began to understand that the philosopher's stone was a myth. They began to study substances not to turn them into gold, but to understand their properties. They began to measure, weigh, record. They began to create chemistry as a science. This was the first great transformation in the history of chemistry, from mysticism to science. From belief that the world consists of 4 elements, to belief that the world consists of atoms. From alchemy to chemistry. But this transition took a long time. It was not a revolution, but an evolution. And it began with doubt. In the 17th century, one man decided to overturn everything that was believed about chemistry. His name was Robert Boyle. Boyle was an English aristocrat, philosopher, and scientist. He was one of the founders of the Royal Society, the world's first academy of sciences. He was the first to say that chemistry should be a science, not a craft or magic. He wrote a book called The Skeptical Chemist, in which he questioned all the basic dogmas of alchemy. Boyle did not believe in the theory of four elements. He did not believe in the idea that all metals consist of sulfur and mercury. He did not believe in the philosopher's stone. He argued that an element is simply a substance that cannot be broken down into simpler components. This was a revolutionary approach. Boyle did not know how many elements existed, but he knew there were more than four. He knew that gold, iron, lead, carbon, sulfur, and phosphorus were different substances, and they could not be reduced to earth, water, air, and fire. Boyle also made important contributions to experimental chemistry. He developed methods for identifying substances by their properties. He studied gases. He discovered the law that relates the volume of a gas to its pressure, Boyle's law. He showed that air is a mixture of gases, not a single substance. He proved that combustion only occurs in the presence of air. Boyle was a skeptic in the best sense of the word. He did not believe anything that could not be tested experimentally. Boyle was also the first to clearly distinguish between chemical elements, compounds, and mixtures. He said that an element is a simple substance that cannot be broken down into simpler ones. A compound is a substance made of two or more elements. A mixture is a mechanical combination of substances. This distinction seems obvious today, but in the 17th century it was a breakthrough. This distinction became the foundation of modern chemistry. Boyle died in 1691. He did not live to see the great discoveries of the 18th century, but he laid the foundation for them. He showed that chemistry could be a science. He showed that experiment was the basis of knowledge. He showed that one could doubt and seek truth. Then came the 18th century, and the revolution began. In the early 18th century, chemists were looking for an explanation of combustion. Why do things burn? What happens when they burn? The German physician Georg Stahl proposed the theory of phlogiston. Stahl argued that all combustible substances contain phlogiston, an invisible element that is released during combustion. When a substance burns, it loses phlogiston. Air is needed to absorb phlogiston. This was an elegant theory. It explained why things burn. It explained why coal and sulfur burn, but gold does not. It explained why metals heated in air turn into calx or rust. This theory was accepted throughout the 18th century. But the phlogiston theory had problems. One of them, when a metal is heated and turns into calx, it becomes heavier. But if it loses phlogiston, it should become lighter. This was a contradiction. Stahl and his followers tried to explain this by saying that phlogiston has negative weight. This was an elegant solution, but it was incorrect. Then came Antoine Lavoisier. Lavoisier was a French aristocrat, chemist and financier. He was one of the brightest minds of his time. He was obsessed with precise measurements. He weighed everything he could weigh. He used balances in his experiments. And he noticed that during combustion, the weight of substances changes. Lavoisier conducted a decisive experiment. He heated mercury in a closed vessel. The mercury turned into mercury calx. The weight of the vessel did not change. But when he heated the calx to a higher temperature, it released a gas. This gas, as it turned out, was the same gas that supports combustion. Lavoisier named it oxygen. He showed that mercury reacts with oxygen to form calx, and when he heats the calx, it decomposes into mercury and oxygen. Lavoisier proved that combustion is a reaction with oxygen. The phlogiston theory was refuted. Lavoisier revolutionized chemistry. He established that the law of conservation of mass always holds. Mass is neither created nor destroyed. It simply changes from one form to another. This was a fundamental principle. Lavoisier showed that chemistry is an exact science. Lavoisier also developed a new chemical nomenclature. He gave names to elements. He described methods of analysis. He wrote a book called Elementary Course in Chemistry, which became the first textbook of modern chemistry. In this book, He defined a chemical element as a simple substance that cannot be broken down into simpler ones. But Lavoisier also had a dark side. He was a tax collector, he was a wealthy man, and in 1794, during the French Revolution, he was arrested. He was accused of conspiring against the people. He was executed by guillotine. Lavoisier was 50 years old. He was a great scientist, but he was also an aristocrat and a capitalist, and the revolution did not forgive him for that. After Lavoisier's death, chemistry continued to develop. His followers strengthened his ideas. The law of conservation of mass became the central principle of chemistry. Chemistry became a science. But the question remained open. What are elements made of? What makes them different? What gives them their properties? This was the next great challenge for chemists. In the early 19th century, the English chemist John Dalton proposed a new theory. Dalton was a modest man, the son of a weaver. He worked as a teacher in Manchester. He was obsessed with meteorology and studied the atmosphere. He noticed that gases mix in certain proportions. He began to study the laws governing these proportions. Dalton noticed the law of multiple proportions. If two elements form several compounds, the masses of one element that combine with a fixed mass of the other are in ratios of small whole numbers. This was an important law. It showed that elements combine in definite proportions. This led Dalton to think that elements consist of atoms. Atoms are tiny, indivisible particles. Atoms of each element have a fixed mass. Atoms combine with each other in simple ratios. Dalton proposed atomic theory. He argued that all substances consist of atoms. Atoms are indestructible. Atoms of the same element are identical. Atoms of different elements differ in mass and properties. Chemical reactions are rearrangements of atoms. Dalton created the first table of atomic weights. He used hydrogen as the basis, taking its atomic weight as 1. This table was crude, but it was a start. It showed that elements have different masses. It showed that atoms are real. Dalton also explained the laws of chemical compounds, the law of definite proportions, formulated by the French chemist Joseph Proust, and the law of multiple proportions. These laws became the foundation of stoichiometry, the branch of chemistry that studies the quantitative relationships between elements in compounds. Stoichiometry was, and remains, the basis of chemical analysis. Dalton's atomic theory became the central paradigm of chemistry for the entire 19th century. It explained many facts. It predicted new discoveries. It was accepted by chemists around the world. But Dalton's atomic theory had shortcomings. Atoms were indivisible particles, but we knew they had structure. Atoms consisted of protons, neutrons, and electrons. This was discovered later. But in the early 19th century, atomic theory was a breakthrough. In 1800, the Italian physicist Alessandro Volta invented the battery, the first source of direct current. Volta's battery consisted of copper and zinc discs separated by cardboard soaked in salt water. This device produced electricity, and chemists immediately began to use it. In 1807, the English chemist Humphry Davy used the battery for electrolysis, the decomposition of substances by electric current. He passed current through molten potassium hydroxide, and he isolated metallic potassium. This was a new element. Davy also isolated sodium, calcium, strontium, barium, and magnesium. All these elements were previously unknown. Davy showed that electricity can decompose substances. He showed that chemical compounds are held together by electrical forces. Davy also discovered the element chlorine. He showed that chlorine is an element. This was important because until then it was believed that chlorine was a compound containing oxygen. Davy showed that chlorine is a simple substance. Davy was one of the first chemists to use electricity to discover new elements. His work inspired other chemists. The Swedish chemist Jöns Jacob Berzelius continued Davy's work. Berzelius was one of the most outstanding chemists of the 19th century. He determined the atomic weights of 45 elements. He developed the system of chemical symbols that we still use today. He introduced the concept of catalysis. He discovered several new elements: selenium, thorium, cerium. Berzelius also developed the electrochemical theory of affinity. He argued that chemical compounds consist of electrically positive and negative parts. This was a correct idea. Berzelius made an enormous contribution to chemistry. In 1811, the Italian physicist Amedeo Avogadro proposed a hypothesis. He argued that equal volumes of gases contain equal numbers of molecules. This was an important hypothesis. It explained the law of combining volumes discovered by Gay-Lussac. It showed that gas molecules consist of atoms, but Avogadro's hypothesis was rejected. The chemists of that time did not understand the difference between atoms and molecules. They believed that gas molecules contained only one atom. This was a mistake. This mistake delayed the development of chemistry for half a century. The Italian chemist Stanislao Canizzaro resolved this dispute. In 1860, at the First International Congress of Chemists in Karlsruhe, he gave a speech defending Avogadro's hypothesis. He showed that it explained all known facts, and he convinced many chemists. The Karlsruhe Congress was a turning point. After it, atomic molecular theory was accepted. Organic chemistry also began to develop. In 1828, Friedrich Wöhler synthesized urea, an organic substance, from an inorganic substance, ammonium cyanate. This was an important experiment. It showed that organic substances could be synthesized in the laboratory. They did not require a vital force. Organic chemistry became a branch of chemistry. By the middle of the 19th century, more than 60 elements had been discovered. Chemists were looking for a system that would organize them. They were looking for a law that would explain their properties, and this law was found. In 1869, the Russian chemist Dmitri Mendeleev published his periodic table. He arranged the elements in order of increasing atomic weight. He noticed that the properties of elements repeat at certain intervals. He created a table in which elements were grouped by properties. Mendeleev left empty spaces in his table. He predicted the existence of new elements that should fill these spaces. He even predicted their properties. This was bold, but his predictions came true. Soon, gallium, scandium, and germanium were discovered, exactly matching his predictions. Mendeleev's periodic law was confirmed. The periodic law is a fundamental law of nature. It shows that the properties of elements depend on their atomic weight, and more precisely, on their nuclear charge. It shows that chemistry is a science of patterns. Mendeleev's periodic table is one of the greatest achievements of the human mind. At the end of the 19th century, a new revolution began. It was connected with the electron and radioactivity. In 1897, the English physicist Joseph John Thomson discovered the electron. He showed that atoms are not indivisible. They contain negatively charged particles. In 1896, the French physicist Henri Becquerel discovered radioactivity. He noticed that uranium salts emit rays that can fog photographic plates. In 1898, Marie and Pierre Curie discovered radium and polonium. They showed that radioactivity is a property of atoms. Radioactive atoms decay, emitting particles. They turn into other elements. In 1903, Ernest Rutherford proposed a model of the atom. He showed that the atom consists of a nucleus and electrons. The nucleus is positively charged. Electrons are negatively charged. This model was confirmed experimentally. In 1911, Rutherford discovered the proton. He showed that the nucleus consists of protons. In 1932, James Chadwick discovered the neutron. The nucleus consists of protons and neutrons. These discoveries changed chemistry. Chemistry ceased to be the science of atoms. It became the science of atomic nuclei. Chemistry and physics merged. A new science emerged: nuclear chemistry. In the early 20th century, physicists developed quantum theory. It explained the structure of the atom. It explained chemical bonds. In 1913, Niels Bohr proposed a model of the atom in which electrons are in specific orbits. He showed that electrons can move from one orbit to another, emitting or absorbing quanta of energy. This model explained the spectra of atoms. It also showed that chemical bonds are formed through the sharing of electrons. In 1926, Erwin Schrödinger developed wave mechanics. He showed that electrons behave not as particles but as waves. Wave mechanics explained the structure of molecules. It became the foundation of quantum chemistry. Quantum chemistry explained the nature of the chemical bond. It showed that atoms join together when their electron clouds overlap. It explained why some compounds are strong and others are not. It explained why some substances conduct electricity and others do not. It explained all the basic properties of substances. The 20th century became the century of synthetic materials. Chemists learned to create substances that do not exist in nature. They created plastic. The first plastic, celluloid, was created in 1869. Then came bakelite, nylon, polyethylene, Teflon. Plastic changed the world. It is cheap, light, and strong. It is used everywhere, from packaging to airplanes. Chemists created synthetic fibers: nylon, polyester, acrylic. These fibers are cheaper and stronger than natural ones. They are used in clothing, carpets, ropes. Chemists created synthetic rubbers. They are used in tires, gaskets, insulation. Chemists created synthetic medicines: aspirin, penicillin, sulfonamides. These medicines saved millions of lives. Aspirin relieves pain and inflammation. Penicillin kills bacteria. Sulfonamides are synthetic antibiotics. Chemists created synthetic fertilizers. They increased agricultural yields. They helped feed a growing global population. The Haber-Bosch process, developed in the early 20th century, allows ammonia to be synthesized from nitrogen in the air. Ammonia is used to produce fertilizers. Without them, half of humanity would have died of starvation. Chemists created new metals: aluminum, titanium, alloys. These metals are light, strong, and corrosion-resistant. They are used in aviation, automotive manufacturing, construction. All these substances were created by chemists. They transformed simple substances, coal, oil, air, water, into useful materials. This was real alchemy. But it was not magic, it was science. Today, chemistry is one of the most dynamic sciences. It is developing faster than ever. Chemists are studying nanomaterials. They are creating molecular machines. They are developing new catalysts. They are synthesizing new medicines. Chemistry is also the key to solving global problems: the energy crisis, climate change, environmental pollution. Chemists are developing new energy sources: solar cells, hydrogen fuel cells. They are developing ways to purify water and air. They are creating biodegradable materials. Chemistry will play an even more important role in the future. It will help us create new materials that are lighter, stronger, and cheaper. It will help us treat diseases that are currently incurable. It will help us build a more sustainable world. But chemistry also carries responsibility. Chemical substances can be dangerous. They can pollute the environment. They can be used to create weapons. Chemists must be careful. They must be aware of the consequences of their discoveries. Alchemists searched for the philosopher's stone. They did not find it. But they learned to transform substances. They learned to turn ore into metals. They learned to turn oil into soap. They learned to turn coal into dyes. They learned to turn oil into plastic. They learned to turn air into fertilizer. They learned to turn atoms into energy. Chemistry is the science of transformations. It is the science of how to make one substance into another. It is the science of how to change the world. Chemistry began with fire and clay. It passed through alchemy, revolution, the atomic age, and the quantum revolution. It became one of the most important sciences in human history. Chemistry is not just a science, it is an art. It is the art of transforming things. It is the art of creating new things. It is the art of understanding the world. It is the art that changed our world. Chemists are the alchemists of the 21st century. They transform one substance into another. They create new materials, new medicines, new sources of energy. They perform miracles. But it is not magic. It is science. Chemistry is the key to understanding the world. It explains what everything around us is made of. It explains how the world works. It helps us improve the world. Without chemistry, there would be no modern medicine, no modern materials, no modern energy, no modern industry. Without chemistry, the world would be very different. It would be poorer, dirtier, more dangerous. Chemistry is a great science. It gives us knowledge that we can use to improve life. It gives us power that we can use for creation. It gives us hope for a better future. This is the greatest lesson of the history of chemistry. Humanity is capable of great transformations. We turned clay into metals. We turned ore into tools. We turned coal into dyes. We turned oil into plastic. We turned air into fertilizer. We turned atoms into energy. We turned knowledge into medicine. And we will continue to transform. We will create new materials. We will create new medicines. We will create new sources of energy. We will create a better future. This ability to transform is what makes us human. It is what makes us creators. It is what makes us chemists. And remember, when you go to sleep tonight, all the atoms in your body were once part of stars. They were created in nuclear reactions that took place in the hearts of stars. They traveled through space, through Earth, through plants and animals to become you. You are the result of nature's great alchemy. You are a child of the stars. And now, rest. Your body is a complex chemical factory that works without stopping. It processes food, produces energy, renews cells. It continues this work even while you sleep. So let it do its work. Let yourself fall asleep. And may the chemistry of your sleep be peaceful and restorative. Good night. In the last part, we left off with John Dalton's atomic theory at the beginning of the 19th century. He showed that all substances consist of atoms, that atoms of each element have their own mass, and that chemical reactions are rearrangements of atoms. This was a brilliant idea that explained many observations, but it raised new questions for chemists. How do you determine the exact atomic weights of elements? How do you know how many atoms of each element are in a compound? And how do you organize the ever-growing number of discovered elements? At the beginning of the 19th century, about 40 elements were known. By the middle of the century, that number had passed 60. Chemists were finding new elements in minerals, in water, in air, in plants. Each new element needed a name, a description, and a place in a system. But what was that system? How do you arrange elements to reflect their properties and relationships? Chemistry resembled a vast library where books were scattered across the floor in disarray. A librarian was needed who could put them on the shelves. And that librarian was Dmitri Mendeleev. But before we get to his great discovery, we need to talk about other important events that happened in chemistry in the first half of the 19th century. Events that prepared the ground for Mendeleev, and without which his table would have been impossible. One such event was the discovery of electricity. In 1800, the Italian physicist Alessandro Volta invented the battery. This was the first source of direct electric current. Volta's battery consisted of copper and zinc discs separated by cardboard soaked in salt water. When the discs were connected by wire, electric current flowed through it. This was a simple device, but it changed the world. Chemists immediately realized that electricity could be used to decompose substances. If you pass current through water, it breaks down into hydrogen and oxygen. If you pass current through a salt solution, you can extract metal. This was exciting. For the first time, chemists could decompose substances not only with fire, but also with electricity. The English chemist Humphry Davy was one of the first to use the battery to discover new elements. Davy was a brilliant experimenter. He was born in 1778 into a poor family in Cornwall. He was self-taught, but his talent was obvious. He became a professor of chemistry at the Royal Institution in London, where he gave his famous lectures, drawing crowds of spectators. In 1807, Davy used the battery to electrolyze molten potassium hydroxide. He passed electric current through the molten substance, and a gleaming metallic bead appeared on one of the electrodes. This was potassium. Davy had isolated a new element that no one had ever seen. Then he isolated sodium, calcium, strontium, barium, and magnesium. All these elements were previously unknown. Davy also showed that electricity can decompose substances into their component parts. He showed that chemical compounds are held together by electrical forces. This was an important discovery. It showed that chemistry and physics are more deeply connected than previously thought. Davy also discovered the element chlorine. Until then, it was believed that chlorine was a compound containing oxygen. Davy showed that chlorine is a simple substance. He was one of the first chemists to use electricity to discover new elements. His work inspired chemists around the world. One of them was the Swedish chemist Jöns Jacob Berzelius. Berzelius was born in 1779. He was one of the most outstanding chemists of the 19th century. He determined the atomic weights of 45 elements with remarkable precision. He developed the system of chemical symbols that we still use today. He introduced the concept of catalysis. He discovered several new elements: selenium, thorium, cerium. Berzelius was painstaking and hard-working. He conducted thousands of experiments to determine the atomic weights of elements. He used Dalton's law of multiple proportions and Proust's law of definite proportions. He carefully weighed substances, measured gas volumes, analyzed results. His table of atomic weights became the standard for chemists around the world. Berzelius also developed the electrochemical theory of affinity. He argued that chemical compounds consist of electrically positive and negative parts. This was a correct idea. It explained why some elements combine easily and others do not. It explained why some compounds are strong and others are weak. Berzelius made an enormous contribution to chemistry. But Dalton's atomic theory had one serious problem. Chemists could not agree on how to determine atomic weights. Dalton believed that water consists of one atom of hydrogen and one atom of oxygen. Other chemists believed that water consists of two atoms of hydrogen and one atom of oxygen. This affected the atomic weights. If water is HO, then the atomic weight of oxygen is about 8. If water is H2O, then the atomic weight of oxygen is about 16. The arguments continued for decades. Chemists could not reach a consensus. This was real confusion. And this confusion needed to be resolved. The Italian chemist Amedeo Avogadro resolved it. In 1811, he proposed a hypothesis that would become the key to solving the problem. Avogadro argued that equal volumes of gases contain equal numbers of molecules. This was a simple and elegant idea. It explained the law of combining volumes discovered by the French chemist Joseph-Louis Gay-Lussac. Gay-Lussac showed that gases combine in simple volume ratios. For example, 1 volume of hydrogen combines with 1 volume of chlorine to form 2 volumes of hydrogen chloride. 2 volumes of hydrogen combine with 1 volume of oxygen to form 2 volumes of water. These ratios were simple and beautiful, but they needed explanation. Avogadro provided that explanation. He said that the volume of a gas is proportional to the number of molecules. If 2 volumes of hydrogen combine with 1 volume of oxygen, this means that 2 molecules of hydrogen combine with 1 molecule of oxygen. Therefore, A hydrogen molecule consists of two atoms, and an oxygen molecule also consists of two atoms, and a water molecule consists of two hydrogen atoms and one oxygen atom. This was a brilliant explanation. It resolved all contradictions. But the chemists of that time did not accept Avogadro's hypothesis. They believed that gas molecules contain only one atom. They did not understand the difference between atoms and molecules. This mistake delayed the development of chemistry for half a century. It was only in 1860, at the First International Congress of Chemists in Karlsruhe, that Avogadro's hypothesis was recognized. The Italian chemist Stanislao Canizzaro gave a speech defending Avogadro. He showed that Avogadro's hypothesis explained all known facts. He convinced many chemists. The Karlsruhe Congress was a turning point. After it, atomic molecular theory was accepted. Chemists finally agreed on how to determine atomic weights. This opened the door to new discoveries. One of the most important consequences of atomic molecular theory was the development of organic chemistry. Organic chemistry studies carbon compounds. Carbon is a unique element. It can form an infinite number of compounds. It can form long chains, branched chains, rings. It can combine with other elements to form complex molecules. In the early 19th century, organic chemistry was limited. Chemists could only analyze simple organic compounds. They could only synthesize a few compounds. But in 1828, something happened that changed everything. Friedrich Wöhler, a German chemist, synthesized urea, an organic substance, from an inorganic substance. He heated ammonium cyanate and obtained urea. This was an important experiment. Until then, it was believed that organic substances could only be created by living organisms using a vital force. Wöhler showed that this was not true. He showed that organic substances could be synthesized in the laboratory. Wöhler's synthesis of urea was a turning point. It broke down the barrier between organic and inorganic chemistry. It showed that chemistry is unified. Organic chemistry became a full branch of chemistry. In the middle of the 19th century, organic chemistry experienced explosive growth. Chemists began to synthesize complex organic compounds. They began to create medicines, dyes, explosives. Organic chemistry became industrial. In 1856, the English chemist William Perkin synthesized Movene, the first synthetic dye. This was an accidental experiment. Perkin was trying to synthesize quinine, a medicine for malaria. He did not get quinine, but he got a purple substance. This substance turned out to be a dye. It was bright, stable, and cheap. Perkin founded a factory to produce Movene. He became the first industrial chemist. Synthetic dyes revolutionized the textile industry. They made clothing brighter and cheaper. They also created a new industry, the chemical industry. But let us return to the main thread of our story. By the middle of the 19th century, more than 60 elements had been discovered. Chemists were looking for a system that would organize them. They were looking for a law that would explain their properties. And this law was found. In 1869, the Russian chemist Dmitri Mendeleev published his periodic table. He arranged the elements in order of increasing atomic weight. He noticed that the properties of elements repeat at certain intervals. He created a table in which elements were grouped by properties. Mendeleev was born in 1834 in Tobolsk, Siberia. He was the 17th child in his family. His father went blind when Mendeleev was young. His mother, a smart and energetic woman, managed a glass factory. She wanted her son to get an education. When Mendeleev was 15, his mother took him to Moscow to enter the university. This was a journey of 1,500 miles by horse-drawn sleigh. In Moscow, Mendeleev was not accepted. So they went to St. Petersburg, and there, after long efforts, Mendeleev was accepted into the Pedagogical Institute. His mother died soon after. Mendeleev was a talented and hard-working student. He graduated from the institute with a gold medal. He taught chemistry at the university. He wrote textbooks. He was obsessed with the idea of order. He wanted to understand how the world is put together. In 1869, Mendeleev was working on the second volume of his textbook, Principles of Chemistry. He had to describe the remaining 55 elements, and he was looking for a way to organize them. One morning, in February 1869, Mendeleev woke up with an idea. He took a sheet of paper and wrote the symbols of the elements on it. He arranged them in order of increasing atomic weight, and he noticed that the properties of elements repeated. This was a revelation. Mendeleev realized that elements could be arranged in a table where each row is a period and each column is a group. In one group, elements have similar properties. Mendeleev created the table. He left empty spaces for elements that had not yet been discovered. He even predicted their properties. This was bold, but his predictions came true. In 1875, the French chemist Lecoq de Bois-Baudran discovered gallium. This was the element that Mendeleev had predicted. He had called it Eka aluminum. The properties of gallium matched Mendeleev's predictions. This was a triumph. Then scandium and germanium were discovered. They also matched Mendeleev's predictions. The periodic law was confirmed. Mendeleev's periodic table became one of the greatest achievements of the human mind. It showed that chemistry is a science of patterns. It showed that the world is logical and understandable. But Mendeleev did not stop there. He continued to work on his table. He refined atomic weights. He corrected mistakes. He predicted new elements. He was confident that his table was a reflection of reality. In 1894, the English physicists Lord Rayleigh and William Ramsay discovered argon, a new element that did not fit into the table. Argon was an inert gas. It did not react with anything. It had no place in the table. Mendeleev was puzzled. He did not know where to put argon, but he did not despair. He realized that argon was the first representative of a new group of elements. He called this group the zero group. Soon, other inert gases were discovered: helium, neon, krypton, xenon, radon. They formed a new group in the table. The periodic table became even more complete and perfect. Mendeleev's periodic table is not just a list of elements. It is a reflection of the structure of matter. It shows that elements are connected to each other. It shows that the properties of elements depend on their atomic weight, and more precisely, on their nuclear charge. The periodic table became the foundation of chemistry. It is used in all areas of chemistry: organic, inorganic, physical, analytical. It helps predict the properties of compounds. It helps synthesize new substances. It helps understand the world. But the periodic table is not only a scientific tool. It is also a symbol of human genius. It shows that the human mind can bring order to chaos. It shows that the world is knowable. It shows that science is the path to truth. At the end of the 19th century, chemistry reached maturity. The periodic table was nearly complete. Atomic molecular theory was confirmed. Chemists could predict the properties of compounds. They could synthesize new substances. They could analyze complex mixtures. Chemistry was a powerful and confident science. But then physics entered the scene. Physicists discovered the electron, radioactivity, quanta. They penetrated deep into the atom. They began to explain chemical bonds. They began to create new models of matter. Chemistry seemed to be retreating. Physics seemed to be absorbing chemistry. Some physicists even said that chemistry was just applied physics, that all chemical phenomena could be explained using physical laws. This was a challenge. Chemists had to respond to it, and they did. They did not deny physics, they integrated it into chemistry. They created new theories that unified chemistry and physics. They created quantum chemistry, chemical physics, molecular biology. They showed that chemistry was not just applied physics, it was an independent science with its own methods, its own theories, its own goals. Chemistry also responded to the challenge by creating new materials. In the 20th century, chemists created more new substances than in all previous history. Plastic, synthetic rubber, nylon, Teflon, Kevlar, carbon fiber, semiconductors, liquid crystals, these are all creations of chemists. These materials changed the world. They created new industries. They created new possibilities. Chemistry became the key science for solving humanity's problems. It was needed for producing food, medicine, energy, materials. It was needed for protecting the environment. It was needed for fighting disease. Chemistry became an integral part of modern life. In the 19th century, organic chemistry was the most dynamic area of chemistry. It studied carbon compounds. Carbon is a unique element. It can form an infinite number of compounds. It can form long chains, branched chains, rings. It can combine with other elements to form complex molecules. Organic chemistry studied these molecules. It studied their structure, their properties, their reactions. In the early 19th century, organic chemistry was limited. Chemists could only analyze simple organic compounds. They could only synthesize a few compounds. But in the middle of the 19th century, a breakthrough occurred. Chemists began to synthesize complex organic compounds. They began to create medicines, dyes, explosives. Organic chemistry became industrial. In 1856, the English chemist William Perkin synthesized movine, the first synthetic dye. This was an accidental experiment. Perkin was trying to synthesize quinine, a medicine for malaria. He did not get quinine, but he got a purple substance. This substance turned out to be a dye. It was bright, stable, and cheap. Perkin founded a factory to produce movine. He became the first industrial chemist. Synthetic dyes revolutionized the textile industry. They made clothing brighter and cheaper. They also created a new industry, the chemical industry. At the end of the 19th century, chemists began to synthesize medicines. They synthesized aspirin, phenacetin, antipyrine. These medicines were effective and cheap. They replaced traditional plant-based remedies. In the early 20th century, chemists began to synthesize plastics. The first plastic was celluloid. It was invented in 1869. It was used for billiard balls, photographic film, toys. Then came bakelite, nylon, polyethylene, Teflon. Plastics changed the world. They replaced wood, metal, glass, rubber. They made objects cheaper and lighter. Organic chemistry became the foundation of the chemical industry. It created new materials, new medicines, new dyes, new fertilizers, new explosives. It changed people's way of life. In the 19th century, inorganic chemistry was less popular than organic chemistry. It studied the compounds of all elements except carbon. It included metals, minerals, acids, bases, salts. It was important for industry, but it was not as exciting as organic chemistry. However, in the 20th century, inorganic chemistry experienced a revival. Chemists began to study new classes of inorganic compounds, complexes, clusters, organometallic compounds. They began to synthesize new materials, semiconductors, superconductors, nanomaterials. They began to apply inorganic chemistry in new areas: catalysis, materials science, medicine. Semiconductors are materials that conduct electricity better than insulators, but worse than conductors. They are the foundation of modern electronics. Transistors, diodes, microchips, all are made from semiconductors. Silicon, germanium, gallium arsenide. These are semiconductors that changed the world. Superconductors are materials that conduct electricity without resistance. They are used in powerful magnets, in power generation, in medical equipment. They could revolutionize energy. Nanomaterials are materials consisting of particles ranging from 1 to 100 nanometers in size. They have unique properties. They can be stronger than steel, lighter than plastic, more chemically active than ordinary materials. They are used in medicine, electronics, Catalysis. Inorganic chemistry became an important science. It creates new materials for the 21st century. In the 20th century, the boundary between chemistry and physics became blurred. Physicists studied the structure of the atom. Chemists studied the structure of molecules. Physicists studied quantum mechanics. Chemists applied quantum mechanics to explain chemical bonds. Physicists studied nuclear reactions. Chemists studied nuclear chemistry. New disciplines emerged: chemical physics, physical chemistry, quantum chemistry. These disciplines combined the methods and theories of chemistry and physics. They studied the structure of matter at the molecular and atomic level. They studied the speed of chemical reactions, kinetics. They studied the thermal effects of reactions, thermodynamics. They studied the structure of molecules, spectroscopy. Quantum chemistry explained the nature of the chemical bond. It showed that atoms join together when their electron clouds overlap. It explained why some compounds are strong and others are not. It explained why some substances conduct electricity and others do not. It explained all the basic properties of substances. Chemical physics studies physical methods for investigating substances. It uses spectroscopy, diffraction, magnetism to study molecular structure. It uses lasers, accelerators, superconductors to create new substances. Chemical physics became an important science. It helped us understand the structure of matter. It helped us create new materials. The 20th century became the century of materials. Chemists created more new materials than in all previous human history. Plastic, synthetic rubber, nylon, Teflon, Kevlar, carbon fiber, semiconductors, liquid crystals. These are all creations of chemists. Plastic is a synthetic polymer. It consists of long chains of molecules. These chains can be flexible or rigid. Plastic can be transparent or opaque, hard or elastic, strong or brittle. Plastic is used everywhere, from packaging to airplanes. It replaced wood, metal, glass, rubber. It made objects cheaper and lighter. Synthetic rubber is an elastomer. It is used in tires, gaskets, insulation. It replaced natural rubber, which was expensive and scarce. Nylon is a synthetic fiber. It is used in clothing, carpets, ropes. It is strong, elastic, light. Nylon replaced natural fibers such as cotton and wool. Teflon is a fluoropolymer. It is resistant to high temperatures, chemicals, and friction. It is used in frying pans, insulation, and the chemical industry. Kevlar is an aramid fiber. It is stronger than steel. It is used in bulletproof vests, ropes, composites. Carbon fiber is a composite. It consists of thin carbon threads bonded with resin. It is stronger than steel and lighter than aluminum. It is used in aviation, automotive manufacturing, and sports equipment. All these materials were created by chemists. They transformed simple substances, coal, oil, air, water, into useful materials. This was real alchemy. At the end of the 20th century, chemistry faced a new challenge: sustainable development. The chemical industry was polluting the environment. Chemical substances were accumulating in soil, water, and air. They were causing disease, poisoning, and climate change. Chemists had to change their methods. They had to create clean technologies. They had to use renewable resources. They had to reduce waste. Green chemistry is a new direction in chemistry. It aims to create chemical products and processes that are safe for the environment. It uses renewable raw materials. It reduces waste. It uses catalysts. It uses safe solvents. It uses efficient synthesis methods. It uses biodegradable materials. Green chemistry has already achieved successes. It has created new catalysts that reduce emissions of harmful substances. It has created new solvents that do not pollute the environment. It has created new polymers that are biodegradable. It has created new synthesis methods that reduce waste. Green chemistry is the future of chemistry. It will help solve environmental problems. It will help create a sustainable economy. It will help preserve the planet for future generations. Chemistry and medicine have always been connected. Alchemists searched for the elixir of life. Chemists created medicines. In the 20th century, chemistry revolutionized medicine. It created new medicines, new diagnostic methods, new treatments. Aspirin was one of the first synthetic medicines. It was synthesized in 1897. It relieves pain, fever, and inflammation. It is used around the world. It saved millions of lives. Penicillin was the first antibiotic. It was discovered in 1928 by Alexander Fleming. It kills bacteria. It saved millions of lives. It changed medicine. Sulfonamides are synthetic antibiotics. They were created in the 1930s. They were effective against many bacteria. They saved millions of lives. Chemotherapy is cancer treatment. It uses chemicals to destroy cancer cells. It was developed in the middle of the 20th century. It saved millions of lives. Diagnostic chemistry uses chemical methods for diagnosis. It uses blood, urine, and tissue analysis to detect diseases. It includes tests for sugar, cholesterol, enzymes, hormones. Molecular biology is the study of molecules responsible for life. It includes DNA, RNA, proteins. It helps understand the mechanisms of heredity, evolution, and disease. Chemistry and medicine are allies. They work together for human health. They create new medicines, new treatments, new diagnostic methods. They make people's lives better. Chemistry and energy have always been connected. Ancient people used fire for heat and light. Chemists studied combustion. Physicists studied heat. In the 20th century, chemistry revolutionized energy. It created new energy sources: nuclear energy, hydrogen fuel cells, solar cells. Nuclear energy is the energy released by splitting atomic nuclei. It is used in nuclear power plants. It generates electricity without carbon emissions, but it creates radioactive waste. Hydrogen fuel cells are devices that convert hydrogen and oxygen into electricity. They produce no harmful emissions. They produce only water. They can be used in cars, power plants, spacecraft. Solar cells are devices that convert sunlight into electricity. They use semiconductors. They produce no harmful emissions. They are a renewable energy source. Biofuels are fuels produced from biomass. They can be used in internal combustion engines. They are a renewable energy source. They reduce greenhouse gas emissions. Chemistry continues to search for new energy sources. It is looking for ways to produce energy from hydrogen, biomass, and sunlight. It is looking for ways to store energy in batteries, fuel cells, and hydrogen. Chemistry is the key to solving energy problems. Chemistry and food have always been connected. Ancient people used fire to cook food. Chemists studied the composition of food. Physicists studied the processes that occur during cooking. In the 20th century, chemistry revolutionized food production. It created new fertilizers, new pesticides, new preservatives, new food additives. Fertilizers are chemicals that increase agricultural yields. They contain nitrogen, phosphorus, and potassium. They help plants grow. They increase food production. Pesticides are chemicals that destroy pests. They protect plants from insects, fungi, and weeds. They increase yields. Preservatives are chemicals that prevent food spoilage. They kill bacteria, fungi, and yeasts. They extend the shelf life of food. Food additives are chemicals that improve the taste, color, smell, and texture of food. They make food more appealing. Chemistry also studies the composition of food. It analyzes the content of vitamins, minerals, proteins, fats, and carbohydrates. It helps create healthy products. It helps fight hunger and malnutrition. Chemistry and the environment are closely connected. Chemicals can pollute the environment. They can accumulate in soil, water, and air. They can cause disease, poisoning, and climate change. Chemists must be careful. They must create safe chemicals. They must develop methods for cleaning the environment. Air pollution is one of the main environmental problems. It is caused by emissions from industrial plants, cars, and power stations. Chemists are developing methods for cleaning air. They are developing catalysts to reduce emissions. They are developing new fuels that do not pollute the air. Water pollution is another environmental problem. It is caused by discharges of industrial waste, agricultural fertilizers, and household waste. Chemists are developing methods for cleaning water. They are developing filters, adsorbents, and reagents to remove pollutants. They are developing methods for biological water treatment. Soil pollution is a third environmental problem. It is caused by the use of pesticides, fertilizers, and industrial waste. Chemists are developing methods for cleaning soil. They are developing methods of phytoremediation, cleaning with plants. They are developing methods of bioremediation, cleaning with microorganisms. Climate change is a global problem. It is caused by emissions of greenhouse gases, carbon dioxide, methane. Chemists are developing methods to reduce emissions. They are developing new energy sources, renewable and nuclear. They are developing methods for capturing and storing carbon dioxide. Chemistry is the key to solving environmental problems. It will help preserve the planet for future generations. Chemistry is the science of transformations. It is the science of how to make one substance into another. It is the science of how to change the world. Chemistry began with fire and clay. It passed through alchemy, revolution, the atomic age, and the quantum revolution. It became one of the most important sciences in human history. Chemistry is not just a science, it is an art. It is the art of transforming things. It is the art of creating new things. It is the art of understanding the world. It is the art that changed our world. Chemists are the alchemists of the 21st century. They transform one substance into another. They create new materials, new medicines, new sources of energy. They perform miracles, but it is not magic, it is science. Chemistry is the key to understanding the world. It explains what everything around us is made of. It explains how the world works. It helps us improve the world. Without chemistry, there would be no modern medicine, no modern materials, no modern energy, no modern industry. Without chemistry, the world would be very different. It would be poorer, dirtier, more dangerous. Chemistry is a great science. It gives us knowledge that we can use to improve life. It gives us power that we can use for creation. It gives us hope for a better future. This is the greatest lesson of the history of chemistry. Humanity is capable of great transformations. We turned clay into metals. We turned ore into tools. We turned coal into dyes. We turned oil into plastic. We turned air into fertilizer. We turned atoms into energy. We turned knowledge into medicine. And we will continue to transform. We will create new materials. We will create new medicines. We will create new sources of energy. We will create a better future. This ability to transform is what makes us human. It is what makes us creators. It is what makes us chemists. And remember, when you go to sleep tonight, all the atoms in your body were once part of stars. They were created in nuclear reactions that took place in the hearts of stars. They traveled through space, through Earth, through plants and animals to become you. You are the result of nature's great alchemy. You are a child of the stars. And now, rest. Your body is a complex chemical factory that works without stopping. It processes food, produces energy, renews cells. It continues this work even while you sleep. So let it do its work. Let yourself fall asleep, and may the chemistry of your sleep be peaceful and restorative. Good night. In the last part, we left off with Dmitri Mendeleev creating his periodic table, which organized all known elements and predicted the existence of new ones. Chemistry seemed to have reached its peak. Scientists knew that there were just over 60 elements, that they obeyed strict laws, and that they could be systematized. But one question continued to trouble the most curious minds. What is an atom really like? What is inside it? And why do some atoms readily combine with others, while some, like the noble gases, remain proudly alone? The answers to these questions did not come from chemists. They came from physicists. And they turned everything people knew about matter upside down. At the end of the 19th century, physicists were studying electricity. They passed current through rarefied gases in glass tubes, and they noticed something strange. When high voltage was applied to the tube, invisible radiation emanated from the negative electrode, which was called the cathode. This radiation made the glass glow green. It cast shadows from objects placed in its path. It was deflected by magnetic fields. Physicists called this radiation cathode rays, but they did not know what it was. Were they waves, like light? Or were they particles, like atoms? The debate continued for decades. In 1897, the English physicist Joseph John Thomson settled this debate. Thomson was a professor of experimental physics at Cambridge University. He was one of the best experimenters of his time. He conducted a series of experiments with cathode rays. Thomson placed two metal plates in the tube. He applied voltage to them, and he saw that the cathode rays were deflected toward the positively charged plate. This meant that the rays consisted of negatively charged particles. Then Thomson measured the deflection of the rays in electric and magnetic fields. He calculated the ratio of the particle's charge to its mass, and he found that this ratio did not depend on the gas in the tube or the material of the electrodes. This meant that the particles making up cathode rays were the same for all substances. Thomson made a bold conclusion. He said that these particles were the fundamental building blocks of matter. He called them electrons. He showed that electrons were 1,000 times lighter than hydrogen atoms. He showed that electrons were part of all atoms. This was a revolutionary discovery. It shattered the idea that the atom was indivisible. It showed that the atom had structure. It opened a new era in science. Thomson proposed a model of the atom. He said that the atom was like a plum pudding. Positive charge was evenly distributed throughout the volume of the atom, like the dough of the pudding. And electrons were embedded in this positive charge, like raisins in the pudding. This was a simple and visual model, but it was incorrect. In 1909, Thomson's student, Ernest Rutherford, conducted an experiment that disproved this model. Rutherford was a New Zealander by birth. He was one of the most brilliant experimenters in the history of science. He worked at Manchester University in England. Rutherford and his students, Hans Geiger and Ernest Marsden, bombarded thin gold foil with alpha particles. Alpha particles are helium nuclei emitted by radioactive substances. They have a positive charge and high speed. According to Thomson's model, alpha particles should have passed through the foil with slight deflections. The positive charge in the atom was evenly distributed, and it could not strongly deflect alpha particles. But the results of the experiment were shocking. Most of the alpha particles passed through the foil without deflection. This was expected. But some alpha particles were deflected at large angles, and a few, though very few, bounced straight back, like a ball off a wall. Rutherford was astonished. He said it was as if you had fired a 15-inch shell at a piece of tissue paper and it bounced back. It was incredible. Rutherford realized that Thomson's model was wrong. He proposed a new model of the atom. He said that the atom consists of a tiny, dense, positively charged nucleus surrounded by electrons. The nucleus contains almost all the mass of the atom. The electrons orbit the nucleus like planets around the sun. This model was revolutionary. It explained the results of the experiment. Alpha particles pass through the atom without deflection because the atom is mostly empty space. But when an alpha particle hit the nucleus, it bounced back because the nucleus was dense and positively charged. Rutherford's model became the basis of the modern understanding of the atom. But it had a problem. According to the laws of classical physics, electrons orbiting the nucleus should radiate energy and fall into the nucleus. The atom should collapse in a tiny fraction of a second. But atoms are stable. They do not collapse. This problem was solved by the Danish physicist Niels Bohr in 1913. Bohr worked in Copenhagen. He was Rutherford's student. He proposed a new model of the atom that combined Rutherford's ideas with new ideas from quantum mechanics. Bohr said that electrons can only be in certain orbits around the nucleus. He called these orbits stationary states. In these orbits, electrons do not radiate energy. They can move from one orbit to another, emitting or absorbing quanta of energy. Bohr's model explained the spectra of atoms. Each element has its own unique spectrum because electrons in its atoms can only move between certain orbits. And each such transition is accompanied by the emission or absorption of light of a specific wavelength. Bohr's model was brilliant. It explained many observations, but it was incomplete. It only worked for hydrogen, the simplest atom. For more complex atoms, it did not work. In 1926, the Austrian physicist Erwin Schrödinger developed wave mechanics. He showed that electrons behave not as particles, but as waves. Wave mechanics explained the structure of all atoms. It became the foundation of quantum chemistry. Quantum chemistry explained the nature of the chemical bond. It showed that atoms join together when their electron clouds overlap. It explained why some compounds are strong and others are not. It explained why some substances conduct electricity and others do not. It explained all the basic properties of substances. But let us return to Rutherford. In 1911, he discovered the proton. He showed that the nucleus of a hydrogen atom consists of a single positively charged particle. He called it the proton. He showed that the nuclei of all elements consist of protons. The number of protons in the nucleus determines the element. This was an important discovery. It explained Mendeleev's periodic table. The atomic number of an element is the number of protons in its nucleus. The properties of the element are determined by the number of protons and electrons. But protons had a problem. The mass of the atom was greater than the sum of the masses of the protons. There must have been other particles in the nucleus. These particles were discovered in 1932 by the English physicist James Chadwick. He called them neutrons. Neutrons have no charge. They have about the same mass as protons. They are in the nucleus along with protons. They hold the nucleus together. The discovery of the neutron completed the picture of the atom. The atom consists of a nucleus containing protons and neutrons, and electrons that orbit the nucleus. The number of protons determines the element. The number of neutrons determines the isotope. This was a great achievement. Humanity finally understood what matter is made of. But it was only the beginning. In 1896, the French physicist Henri Becquerel discovered radioactivity. He noticed that uranium salts emit rays that can fog photographic plates. This was an accidental discovery. Becquerel placed uranium salt on a photographic plate wrapped in black paper. He put it in a drawer and forgot about it. A few days later, he developed the plate and saw a spot on it. Uranium was emitting rays that passed through the paper. Becquerel did not know what these rays were. He thought they were similar to X-rays, which had been discovered the year before. But he was wrong. The rays emitted by uranium were a different kind of radiation. Marie and Pierre Curie began to study radioactivity. Marie Curie was Polish by birth. She came to Paris to study. She was a brilliant student. She married Pierre Curie, a French physicist. The Curies investigated uranium ore. They noticed that the ore was more radioactive than pure uranium. This meant that there were other radioactive substances in the ore. They began to isolate these substances. In 1898, the Curies discovered two new elements, polonium and radium. Polonium was named after Poland, Marie's homeland. Radium was named from the Latin word for ray. Radium was incredibly radioactive. It emitted rays that were visible in the dark. It emitted heat. It destroyed living tissue. The Curies did not know about the dangers of radiation. They worked with radium without protection. They carried test tubes of radium in their pockets. They suffered from burns and illnesses. Marie Curie died of aplastic anemia caused by radiation exposure. She was buried in a lead-lined coffin. Her notes are still radioactive. They can only be studied in protective suits. Radioactivity was an important discovery. It showed that atoms are not stable. They can decay. They can turn into other elements. This was alchemy in reality. Rutherford and Frederick Soddy showed that radioactive decay is the transformation of one element into another. When a uranium atom emits an alpha particle, it turns into a thorium atom. When a radium atom emits an alpha particle, it turns into a radon atom. This was an amazing discovery. It explained why radioactive substances emit radiation. Radioactivity also had practical applications. It was used in medicine to treat cancer. It was used in industry for quality control. It was used in science to study the structure of matter. But radioactivity also had a dark side. It was used to create atomic bombs. It was used to produce energy. It created radioactive waste that is dangerous to the environment. In 1938, the German chemists Otto Hahn and Fritz Strassmann discovered nuclear fission. They bombarded uranium with neutrons, and they found that uranium decayed into lighter elements such as barium and krypton. This was an amazing discovery. It showed that the atomic nucleus could be split. Lisa Meitner, an Austrian physicist, explained nuclear fission. She showed that enormous amounts of energy are released during fission. She used Einstein's equation E equals mc squared. She showed that the mass of the fission products was less than the mass of the original nucleus. The difference in mass was converted into energy. Nuclear fission became the basis for creating the atomic bomb and nuclear power plants. It changed the world. It created new possibilities and new threats. In 1945, the United States dropped atomic bombs on Hiroshima and Nagasaki. These were the first and only uses of nuclear weapons in war. They killed hundreds of thousands of people. They showed the destructive power of the atom. After the war, nuclear energy was used for peaceful purposes. Nuclear power plants were built. They generated electricity without greenhouse gas emissions. But they also created radioactive waste that had to be stored for thousands of years. Nuclear energy was controversial. Some saw it as the solution to energy problems. Others saw it as a threat to humanity. The debate continues to this day. At the end of the 20th century, physicists and chemists joined forces. They created a new science, nuclear chemistry. Nuclear chemistry studies the structure and properties of nuclei. It studies nuclear reactions. It studies radioactivity. Nuclear chemistry has many applications. It is used in medicine for diagnosis and treatment. It is used in industry for quality control and materials analysis. It is used in science to study the structure of matter. But nuclear chemistry also raises new questions. How do you control nuclear reactions? How do you store radioactive waste? How do you prevent nuclear war? These questions need answers. We have traced the path of chemistry from the first fires to the nuclear age. We have seen how alchemy became science, how atoms and molecules were discovered, how electricity and quantum mechanics overturned our understanding of matter, how the structure of the atom and nuclear reactions were discovered. But the story does not end here. In the 20th century, chemistry faced a new challenge, creating new materials that would change the world. Plastic, nylon, Teflon, Kevlar, semiconductors. All these materials were created by chemists. They changed our lives. They created new industries. They opened new possibilities. And now, rest. Your body is a complex chemical factory that works without stopping. It processes food, produces energy, renews cells. It continues this work even while you sleep. So let it do its work. Let yourself fall asleep. And may the chemistry of your sleep be peaceful and restorative. Good night. In the last part, we traced how physicists penetrated deep into the atom, discovering the electron, the nucleus, the proton, and the neutron, how quantum mechanics explained the nature of the chemical bond, and how nuclear reactions showed that alchemy was not a myth, but a reality hidden in the depths of the atom. Chemistry seemed to have reached its limit. It knew what substances were made of. It knew how they combined. It knew how they broke apart. But this was only the beginning. The real revolution came when chemists realized that knowledge of the structure of atoms and molecules gave them incredible power. The power to create what does not exist in nature. The power to transform simple substances into complex materials with new properties. The 20th century became the century of synthetic materials. Chemists created more new substances than in all previous human history. Plastic, synthetic rubber, nylon, Teflon, Kevlar, carbon fiber, semiconductors, liquid crystals. All these materials were created in laboratories. They changed the world in ways that no empire, no revolution, no war could match. But to understand how this happened, we need to go back to the middle of the 19th century, to the time when chemists were just beginning to understand that organic compounds could be created artificially. As we remember, in 1828, Friedrich Wöhler synthesized urea from inorganic substances. This was the first step. But no one at the time could foresee where this step would lead. In 1856, the English chemist William Perkin was working on synthesizing quinine, a medicine for malaria. Quinine was expensive and rare. It was obtained from the bark of the cinchona tree, which grew only in South America. Europe needed cheap and accessible quinine. Perkin tried to produce it synthetically. He used aniline, a substance obtained from coal tar. Coal tar was a waste product of gas production. There was a lot of it, and it was cheap. Perkin heated aniline with various reagents. He hoped to get quinine. Instead, he got a dark, oily liquid. He was disappointed. But then he noticed that this liquid dyed fabric a bright purple color. It was a dye. Perkin named it movine. Movine was the first synthetic dye. It was bright, stable, and cheap. It caused a real revolution in the textile industry. Before this, fabrics were dyed with natural dyes, indigo, madder, kermes. They were expensive and not always stable. Synthetic dyes were cheaper and better. Perkin founded a factory to produce movine. He became the first industrial chemist. His factory made enormous profits. Movine became fashionable. It was worn by royalty and common people alike. But Perkin made another important discovery. He showed that chemistry could create new substances that did not exist in nature. He showed that chemistry could compete with nature. This was a turning point. Soon after Perkin, chemists began to synthesize other dyes. They learned to produce alizarin, a red dye previously obtained from the root of the madder plant. They learned to produce indigo, a blue dye previously obtained from plants. They learned to produce hundreds of different dyes in all colors and shades. The textile industry flourished. Clothing became brighter and cheaper. Poor people could afford clothing that had previously been available only to the rich. This was a social change brought about by chemistry. But dyes were only the beginning. Chemists realized that coal tar was not just waste. It was a treasure trove of new substances. They began to investigate its composition. They discovered benzene, toluene, naphthalene, anthracene, simple aromatic hydrocarbons. They learned to transform them into complex organic compounds. In 1869, chemists obtained the first synthetic pharmaceutical, phenacetin. This was a medicine for fever and pain. Then came aspirin, one of the most famous medicines in history. Aspirin was synthesized in 1897 by the German chemist Felix Hoffmann, who worked for the Bayer Company. Hoffmann was trying to find a medicine for his father, who suffered from arthritis. He synthesized acetyl salicylic acid, which he named aspirin. Aspirin was effective and safe. It relieved pain, fever, and inflammation. It became the best-selling medicine in the world. It is still used today. But chemistry was not limited to dyes and medicines. It penetrated other industries. It created new materials that changed the world. One such material was plastic. Plastic is a synthetic polymer. It consists of long chains of molecules called polymers. Polymers can be flexible or rigid, transparent or opaque, hard or elastic. The first plastic was created in 1869 by the American chemist John Hyatt. He was looking for a substitute for ivory to produce billiard balls. Ivory was expensive and scarce. Hyatt mixed nitrocellulose with camphor and obtained a hard, durable material called celluloid. Celluloid was the first thermoplastic. It could be melted when heated and hardened when cooled. It could be molded and colored. It was used to produce billiard balls, photographic film, toys, combs, collars. Celluloid was successful, but it was flammable. It could catch fire from a spark. This was dangerous. Chemists were looking for a safer material. In 1907, the Belgian chemist Leo Baekeland created a new plastic, Bakelite. Bakelite was a thermosetting plastic. It did not melt when heated. It was hard, strong, and non-flammable. Bakelite caused a revolution. It was used to produce electrical insulators, telephone handsets, radios, knife handles. Bakelite was the first synthetic plastic that replaced metal, glass, and wood. Then came new plastics: polyethylene, polypropylene, polystyrene, polyvinyl chloride. Each had unique properties. Polyethylene was flexible and strong. It was used for bags, bottles, pipes. Polypropylene was rigid and chemical resistant. It was used for car parts, appliance housings, carpets. Polystyrene was light and transparent. It was used for packaging, toys, appliances. Polyvinyl chloride was strong and fire-resistant. It was used for pipes, cables, coatings. Plastics changed the world. They made objects cheaper, lighter, and stronger. They replaced wood, metal, glass, and rubber. They created new industries, but plastics also created new problems. They do not decompose in nature. They pollute oceans and soil. They release toxic substances when burned. They are a threat to the environment. Chemists are looking for a solution to this problem. They are developing biodegradable plastics. They are creating plastics from renewable raw materials. They are developing recycling methods for plastics. This is one of the main tasks of modern chemistry. Another important material was synthetic rubber. Natural rubber was obtained from the milky sap of the rubber tree. It was expensive and scarce. During World War II, when Japan seized rubber plantations, the Allies were left without rubber. This created serious problems for the war industry. Chemists found a solution. They developed methods for synthesizing rubber from butadiene, which was obtained from oil. Synthetic rubber was as good as natural rubber. It was strong, elastic, and wear-resistant. Synthetic rubber was used to produce tires, gaskets, insulation. It became the foundation of the automotive industry. Without synthetic rubber, there would be no modern transportation. Then came new synthetic fibers. Nylon was created in 1935 by the chemist Wallace Carruthers at the DuPont Company. Nylon was the first synthetic fiber that surpassed natural fibers in strength, elasticity, and wear resistance. Nylon was used for stockings, clothing, carpets, ropes, parachutes. During World War II, nylon was used for parachutes and tires. Nylon saved many lives. Then came other synthetic fibers: polyester, acrylic, spandex. They are used in clothing, carpets, furniture, technical textiles. They are cheaper and stronger than natural fibers. One of the most amazing materials was Teflon. It was discovered by accident in 1938 by the chemist Roy Plunkett. Plunkett was working on creating a new refrigerant. He stored compressed tetrafluoroethylene gas in cylinders. When he opened the cylinder, the gas did not come out. Plunkett cut open the cylinder and found a white powder inside. This was polytetrafluoroethylene, which became known as Teflon. Teflon was an amazing material. It was resistant to high temperatures, chemicals, and friction. It was slippery and impermeable. It was used for non-stick coatings for frying pans, wire insulation, gaskets in the chemical industry. Teflon became a symbol of modern chemistry. Another amazing material was Kevlar. It was created in 1965 by the chemist Stephanie Kwolek at the DuPont Company. Kevlar was an aramid fiber that was 5 times stronger than steel for the same weight. It was used for bulletproof vests, ropes, composites. Kevlar saved many lives. Carbon fiber was another amazing material. It consisted of thin carbon threads bonded with resin. It was stronger than steel and lighter than aluminum. It was used in aviation, automotive manufacturing, and sports equipment. Carbon fiber changed the design of airplanes, cars, and bicycles. But chemistry was not limited to organic materials. It also created new inorganic materials that changed the world. One of these was semiconductors. Semiconductors are materials that conduct electricity better than insulators, but worse than conductors. They are the foundation of modern electronics. Transistors, diodes, microchips, all are made from semiconductors. The main semiconductor material is silicon. It was discovered in 1824 by the Swedish chemist Jöns Jacob Berzelius. But no one knew about its properties at the time. In the middle of the 20th century, physicists and chemists began to study silicon. They discovered that it had unique electrical properties. It could be a conductor or an insulator, depending on temperature and impurities. This discovery led to the creation of the transistor in 1947. The transistor was invented by the American physicists William Shockley, John Bardeen, and Walter Brattain. It replaced bulky and unreliable vacuum tubes. The transistor became the foundation of modern electronics. It is used in computers, phones, televisions, radios, medical equipment. Without the transistor, there would be no internet, no smartphones, no artificial intelligence. Then came integrated circuits. They were invented in 1958 by Jack Kilby and Robert Noyce. Integrated circuits combine thousands, millions, billions of transistors on a single silicon chip. They are the brain of modern computers. Moore's law, formulated by Gordon Moore in 1965, states that the number of transistors on an integrated circuit doubles approximately every 2 years. This law held for several decades. It led to exponential growth in computing power. But exponential growth cannot continue forever. Transistors are becoming smaller and smaller. Today they are only a few nanometers in size. At this size, quantum effects begin to affect their operation. Chemists and physicists are looking for new materials and new approaches. They are investigating graphene, carbon nanotubes, organic semiconductors. They are creating new materials for the next generation of electronics. Another important inorganic material was superconductors. Superconductors are materials that conduct electricity without resistance at low temperatures. They were discovered in 1911 by the Dutch physicist Heike Kamerlingh-Onnes. Superconductors are used in powerful magnets for medical MRI machines, in particle accelerators, in power generation. They could revolutionize the transmission of electricity, making it more efficient. But superconductors require very low temperatures, close to absolute zero. This is expensive and complicated. Chemists are looking for new superconductors that work at room temperature. This is one of the most exciting areas of modern chemistry. Nanomaterials are another area where chemistry is revolutionizing the world. Nanomaterials consist of particles ranging from 1 to 100 nanometers in size. They have unique properties that differ from those of ordinary materials. Gold nanoparticles, for example, are red or blue in color, unlike the yellow color of ordinary gold. Nanoparticles can be used in medicine to deliver drugs to cancer cells. They can be used in electronics to create faster and more efficient devices. They can be used in catalysis to speed up chemical reactions. Carbon nanotubes are one of the most famous nanomaterials. They consist of sheets of graphene rolled into tubes. They have amazing strength and electrical conductivity. They can be used in composites, electronics, medicine. Graphene is another amazing nanomaterial. It consists of a single layer of carbon atoms arranged in a honeycomb pattern. It has unique electrical, mechanical, and thermal properties. It can be used in electronics, energy, biology. Nanomaterials chemistry is a rapidly developing field. Chemists are creating new nanomaterials with specific properties. They are investigating their applications in various fields. But chemistry not only creates new materials, it also helps us use already known materials more efficiently. One example is catalysis. Catalysts are substances that speed up chemical reactions but are not consumed themselves. They are used in industry to produce thousands of products. Catalysts are used to produce gasoline, plastics, medicines, fertilizers. They are used to clean car exhaust. They are used to synthesize new materials. Chemists are developing new catalysts that are more efficient and selective. They are using nanoparticles as catalysts. They are creating catalysts that work at lower temperatures and pressures. This makes industrial processes more economical and environmentally friendly. Chemistry also helps us in medicine. Chemists synthesize new medicines that save lives. They create new diagnostic methods. They develop new treatments. Penicillin, the first antibiotic, was discovered in 1928 by Alexander Fleming. It saved millions of lives. Since then, chemists have synthesized many antibiotics that treat various infections. Chemotherapy is the treatment of cancer with chemicals. It was developed in the middle of the 20th century. It saved millions of lives. Chemists synthesize new anti-cancer drugs that are more effective and have fewer side effects. Aspirin, penicillin, chemotherapy. These are all achievements of chemistry. Chemistry makes us healthier and helps us live longer. But chemistry also raises new questions. How do we synthesize new medicines faster and cheaper? How do we defeat diseases that have not yet been defeated? How do we use chemistry to fight pandemics? Chemistry is the science of transformations. It began with fire and clay. It passed through alchemy, revolution, the atomic age, and the quantum revolution. It became one of the most important sciences in human history. Chemistry created new materials that changed the world. It created plastic, synthetic rubber, nylon, Teflon, Kevlar, semiconductors, nanomaterials. These materials are used in all areas of life. They make our lives more comfortable, safer, and more interesting. Chemistry created new medicines that save lives. It created antibiotics, chemotherapy, vaccines. It makes us healthier and helps us live longer. Chemistry created new sources of energy. It created nuclear energy, hydrogen fuel cells, solar cells. It helps us fight climate change. Chemistry is the key to solving global problems. It will help us create a sustainable future. It will help us preserve the planet for future generations. We have traced the path of chemistry from the first fires to modern materials. We have seen how alchemy became science, how atoms and molecules were discovered, how electricity and quantum mechanics overturned our understanding of matter, how chemistry created new materials that changed the world. But the story does not end here. Chemistry continues to develop. It is creating new materials, new medicines, new sources of energy. It is solving global problems. It is building the future. And now, rest. Your body is a complex chemical factory that works without stopping. It processes food, produces energy, renews cells. It continues this work even while you sleep. So let it do its work. Let yourself fall asleep. And may the chemistry of your sleep be peaceful and restorative. Good night. We have come a long way, from the first fire kindled in a prehistoric cave to the most sophisticated laboratories of the modern age, from belief in 4 elements to understanding the quantum nature of chemical bonds, from alchemists searching for the philosopher's stone to chemists creating materials that do not exist in nature. The history of chemistry is a history of transformations, but it is not finished. And perhaps the most exciting chapter of this story is being written right now. In this final part of our journey, we will look ahead. We will see how chemistry is responding to the greatest challenges of our time: climate change, environmental pollution, resource depletion. We will learn about green chemistry, which aims to make chemical processes safe and sustainable. We will see how chemists are fighting forever chemicals that poison our world. And we will understand that the philosopher's stone, which alchemists sought for so long, has finally been found, not as a magical substance, but as knowledge that allows us to turn waste into resources and pollution into purity. Chapter 16. Green Chemistry. A new vision for an old science. In previous parts, we saw how chemistry changed the world. It gave us medicines that saved millions of lives. It gave us materials from which the modern world is built: plastic, nylon, Teflon, semiconductors. It gave us fertilizers that fed a growing global population. Without chemistry, our world would be very different: poorer, hungrier, sicker. But this progress had a dark side. The chemical industry turned out to be one of the main polluters of the environment. Toxic waste, greenhouse gas emissions, depletion of natural resources. All this became the price we paid for chemical progress. And at the end of the 20th century, chemists began to realize that this could not continue. Thus, green chemistry was born. It is not just a set of technologies, it is a new way of thinking. It is an approach that says, we can create the substances we need without harming the planet. It is a philosophy that asserts that chemistry should be not part of the problem, but part of the solution. In 1998, chemists Paul Anastas and John Warner formulated 12 principles of green chemistry. These principles became the manifesto of a new approach. They proclaimed that it is better to prevent waste than to clean it up afterwards, that renewable raw materials should be used instead of non-renewable ones, that catalysts are better than stoichiometric reagents, that chemical processes should be safe and energy efficient. These principles were simple and clear, but implementing them turned out to be a difficult task. The chemical industry is a huge, inert mechanism. It was built over decades on certain methods and raw materials. Rebuilding it is like turning an aircraft carrier in a narrow canal. And yet, change began. Today, green chemistry is no longer a marginal movement. It is a recognized field that is developing around the world. There are scientific journals devoted exclusively to green chemistry. The largest chemical companies are creating sustainability departments. Governments are introducing environmental standards and subsidizing green technologies. But this is not enough. As recent studies show, the 12 principles of green chemistry formulated more than a quarter of a century ago need updating. The world has changed. The climate crisis has become a reality. Forever chemicals are found in the blood of almost every person on the planet. and old approaches no longer seem sufficient. Modern researchers are calling for a modernization of the principles of green chemistry. Not because the old principles were bad, but because they were too soft, too optional. Instead of prevent waste, we need to say, do not create waste. Instead of use renewable raw materials, must use renewable raw materials. Green chemistry should become not a recommendation, but a requirement. Chapter 17. PFAS. Forever chemicals and their curse. There is no better example of how chemistry created a problem that it now must solve than the story of PFAS. PFAS are per- and polyfluoroalkyl substances. In everyday language, they are called forever chemicals. And this name is no exaggeration. These molecules were developed in the middle of the 20th century. They had amazing properties: resistance to water, to grease, to high temperatures. They were added to non-stick frying pans, to waterproof clothing, to fast food packaging, to firefighting foam. It seemed that humanity had found ideal materials, but therein lay the problem. PFAS turned out to be too stable. The bond between carbon and fluorine atoms, which gives them their properties, is one of the strongest in chemistry. It does not break down in nature. It does not break down in water. It does not break down in soil. It accumulates in the bodies of animals and humans. Today, PFAS are found in the blood of almost every person on Earth. They are found in drinking water, in fish, in breast milk. They are associated with immune disorders, thyroid problems, and some types of cancer, and they are not going anywhere. The problem is that PFAS do not decompose, explains chemist Vincent Courset from the Collège de France. In nature, they accumulate everywhere, even in the drinking water of some regions. The levels exceed permissible limits. What can be done? Conventional water treatment methods do not work. PFAS require temperatures above 1,000 degrees Fahrenheit to break down. This is expensive and inefficient, but chemists are looking for a solution. One promising direction is silicon chemistry. Silicon is the element that sits directly below carbon in the periodic table. It has similar chemical properties, but with important differences. Silicon is cheaper and more environmentally friendly than many metals traditionally used in chemistry, and it can activate strong bonds, including the very carbon-fluorine bond that makes PFAS so stable. If we can remove the fluorine atoms that make up PFAS, we can create something much less dangerous and much easier to process, says Courset. Our goal is not to destroy them, but to recycle them. These elements remain a source of carbon that can be recovered. This is an approach that fully corresponds to the spirit of green chemistry, not just to dispose of waste, but to turn it into resources. Not to fight pollution, but to create cycles where the waste of one process becomes the raw material for another. Chapter 18. Nature as teacher. But perhaps the most important lesson that chemistry must learn is the lesson of nature. Nature has been doing chemistry on Earth for 4 billion years, and in all that time, it has not used a single drop of oil. All chemical reactions in nature occur either without solvents or in water, using soft matter, membranes, bubbles, micelles. Human chemistry, by contrast, is almost entirely dependent on oil. As raw material, as solvents, as fuel, oil is a non-renewable resource, and one day it will run out. But even more important, burning petroleum products is the main cause of climate change. Organic chemistry still has an image of being a highly polluting field, notes Courset. It is extremely important to change practices in order to change the perception of the general public. Nature defines efficiency on its own terms. It does not use complex catalysts made from expensive metals that are difficult to mine. It does not use toxic solvents. It works at room temperature and atmospheric pressure. And it produces amazingly complex molecules that humans cannot yet synthesize in the laboratory. chemists are beginning to learn from nature. They are creating catalysts based on more accessible metals, nickel, copper, cobalt. Or they are abandoning metals altogether in favor of silicon. They are developing reactions that can be carried out in water. They are looking for ways to use renewable raw materials, vegetable oils, cellulose, agricultural waste. Chapter 19: Energy and Sustainability. Chemistry plays a key role in the transition to sustainable energy. Solar cells work thanks to semiconductor chemistry. Hydrogen fuel cells convert hydrogen and oxygen into electricity, producing only water. New types of batteries allow us to store energy obtained from the sun and wind. But even here, there are challenges. Lithium-ion batteries, which power our phones and electric cars, depend on lithium and cobalt. Mining these metals is often associated with serious environmental and social problems. Chemists are looking for new materials for batteries, cheaper, more abundant, safer. Sodium-ion batteries, magnesium batteries, organic batteries. All of these are being actively developed, and all of them require a deep understanding of chemistry. Chapter 20: Medicine of the Future. Chemistry continues to save lives. New medicines, new diagnostic methods, new approaches to treatment, all of these are the result of the work of chemists. But in the 21st century, medicine is becoming personalized. Medicines are developed for a specific patient, not for an abstract, average disease. This requires a new level of understanding of chemistry. Molecular biology, genetics, proteomics, all of these fields depend on chemical methods. Chemists are creating new molecules for targeted therapy, for diagnosis, for drug delivery. And again, green chemistry plays a role. The pharmaceutical industry is one of the most polluting, but even here, changes are happening. Chemists are developing more efficient syntheses that produce less waste. They are using enzymes instead of chemical catalysts. They are creating medicines that break down in the body in a safe way. Chapter 21: Lessons of History. Looking back at the long path we have traveled, one pattern can be seen. Chemistry has always been the science of transformations. Alchemists searched for the philosopher's stone to turn lead into gold. 19th century chemists learned to turn coal into dyes and medicines. 20th century chemists turned oil into plastic and created atomic energy. And today, chemistry is undergoing a new transformation. It is turning from a science of creation into a science of restoration. From a science of consumption into a science of sustainability. From part of the problem into part of the solution. This does not mean that chemistry is abandoning its achievements. Medicines will remain, materials will remain, energy will remain. But the methods of obtaining them are changing. Instead of oil, biomass. Instead of toxic solvents, water. Instead of expensive metals, more accessible alternatives. And of course, chemistry will continue to create new things. New materials for electronics, for medicine, for energy. New ways to fight disease and pollution. New knowledge about how the world works at the deepest level. Epilogue: The Philosopher's Stone Found. When we began this journey, we stood by the fire with a prehistoric man who first saw a stone turn into metal. We passed through alchemical laboratories where they searched for the philosopher's stone. We stood next to Lavoisier as he weighed substances and discovered oxygen. We watched Mendeleev create his table in a dream. We penetrated deep into the atom with Rutherford and Bohr. We saw chemistry create the modern world from plastic, nylon, and medicines. And now we know that the philosopher's stone was found. It turned out not to be a magical substance, but knowledge. Knowledge about how matter is structured. Knowledge about how to transform one substance into another. Knowledge about how to create new things without destroying the old. Chemistry is a story of transformations, and it continues. Every day, chemists create new molecules that have never existed in nature. Every day they find new ways to use old materials. Every day they come closer to solving the most complex problems of humanity. And when you go to sleep tonight, remember this. In every atom of your body lies the history of millions of years of stellar evolution. In every molecule lies the result of the work of thousands of chemists who lived before us. And in every new day lies the opportunity for new transformations. You are a child of the stars. You are the result of nature's great alchemy, and you are part of the future that chemistry is helping to build. And now, rest. Your body is a complex chemical factory that works without stopping. It processes food, produces energy, renews cells. It continues this work even while you sleep. So let it do its work. Let yourself fall asleep, and may the chemistry of your sleep be peaceful and restorative.